Everywhere you look today, something is suddenly powered by AI. Writing essays, generating images, composing music, beating world class chess players, diagnosing medical scans, summarizing entire books. It all feels like magic. And what's even stranger is that all of these problems are completely different from each other. Some are classification problems, some prediction, some clustering, and some generate new things, while some can even understand language. So you'd think that the algorithms behind them must also be completely different. And they technically are. But here's the wild part. All of these wildly different AI systems, almost every major model you've heard of, relies on one shockingly simple algorithm. And most videos about how AI works never really talks about it. So today, we're going to. Before I reveal the algorithm, I want to change how you think about AI. Most people imagine AI as something that magically predicts the correct output. But that's not what's actually happening. A better way to think about it is this: AI is trying to find a function that can predict the output. AI is not guessing the output directly. Instead, AI is building a function that, when given an input, can produce the correct output, or at least the best possible guess. So, training an AI is not making it smarter. Instead, training is essentially guessing a function, checking if it's good, and then modifying the function, trying to make it better, and then checking how good it is again, and repeating the process until we just decide that this is the best function that we're going to go with. And that's it. So it definitely needs to know whether the function is actually good to check if the function is working or not. And sometimes it knows the correct answer. For example, this image is a dog, or this house sold for so and so amount of money, or this sentence translates to this other sentence in a different language. This is called supervised learning. The AI can clearly measure how wrong it is. But sometimes there is no correct answer, like grouping similar customers or detecting anomalies in credit card transactions. There is no right answer, but we can still define a number that represents how bad the grouping currently is. And that number, which is like the wrongness, is what we call the loss. And now here's the key. Whether the task is supervised or unsupervised, AI improves the function by trying to reduce the loss. So the real question becomes, how does an AI modify the function so that the loss gets smaller? And that is where our algorithm finally enters. Let's imagine the function that the AI is trying to optimize has only two parameters that it can adjust, like two knobs that it can turn. If we plot the loss for every possible combination of those two parameters, we would get a surface, something like a landscape. The high areas would correspond to a bad function because it has high loss, and low areas would correspond to a better function, which is because it would have a low loss. Somewhere on that surface is going to be the lowest point, which is going to be the best possible function. The problem? You cannot calculate the loss for every single point on the surface. Even with only two parameters, that's already expensive. And real AI doesn't have just two parameters. ChatGPT has over 1 trillion. Finding the absolute minimum by brute force is literally impossible. So instead, we use a beautifully clever idea. Imagine you're standing in a hilly terrain that's covered in a thick fog. You can't see any mountains in the distance. In fact, the only thing that you can see is the patch of ground right around your feet. Your goal is to get to the lowest point in the valley. So, how would you do it? Essentially, you would feel the slope of the ground underneath your feet. You would look for the direction where the ground seems to be going down, and then you would take a small step in that direction. And then you would repeat this process again and again. Eventually, you would reach a point where every direction seems to be going upward. And that is the bottom, the best possible place that you can reach. This process is literally gradient descent. Just like how you checked the slope of the ground, AI checks the gradient. The gradient is similar to the slope of a function, except when it's in multiple dimensions. So the gradient tells you the direction where the loss begins to increase the fastest. So you're going to do the opposite. You move your parameters in the negative direction of the gradient. And that's how it gets its name, gradient descent. So you update the parameters and then you calculate the gradient again, and then you update the parameters once again, and you repeat this process thousands, millions, and sometimes even billions of times. And that is how the AI improves. But a very important thing to note is that the size of each step matters. If you take steps that are too small, it will literally take you forever to reach the bottom. And if you take steps that are too big and you start jumping around, you might jump over the valley and bounce around wildly without ever settling. And when training an AI, this is called instability, and it's a real problem. So researchers created smarter variations like adaptive learning rates, ADAM, RMS prop, and even things like momentum, which is where it lets the AI keep moving in a consistent direction, smoothing out small bumps and speeding through long slopes. It's like pushing a heavy shopping cart. Once it's rolling, small bumps don't stop it. But deep down, all of these algorithms are doing the same thing. They use the gradient, but they take different and smarter steps. Now, some people might ask, why not just compute the derivative and solve for the minimum directly like we used to do back in high school calculus? And the reason we can't do that is because in deep learning, we're not talking about functions of two variables. We're talking about millions or trillions of variables. Finding the double derivative or the minima of a function in just three variables itself or three dimensions becomes increasingly complicated. And here, as we've stated before, there could be millions or trillions of parameters, which means it would have to find the minima in a trillion dimensional equation. The math is incomprehensibly complex. Gradient descent works because it doesn't try to solve the whole problem perfectly. It just moves towards what it thinks is better, over and over until it's good enough. Now, some of you might have noticed from the example that there were many valleys, not just one. And sometimes we end up in a local minimum instead of a global minimum. And originally, researchers thought that this would make gradient descent useless. But in practice, the local minima are good enough to power nearly everything you've seen AI do. We don't know why it works so well, but it does. Gradient descent doesn't give us the perfect answer, but it gives us an answer that works. Gradient descent isn't just math, it's a mindset. It doesn't wait until it understands everything. It doesn't freeze because the solution is uncertain. It doesn't panic because the landscape is too complicated. It just looks around and moves one informed step at a time in the best direction that it can see. And somehow, over time, that itself becomes intelligence. We saw the same philosophy in the Kalman filter. Predict your best estimate, see what the error is, and update. Similarly, in Monte Carlo, we saw that even if you can't compute the accurate results, you can sample a small random number and just average the results to get the best estimate that you possibly can, which closely resembles reality. We see the same thought process here again. You don't need perfection to make progress. You just need direction and small steps. So the next time you see AI doing something incredible, whether it's writing, composing, diagnosing, or anything else, remember, it's all learning one small step at a time, just like we do. Gradient descent is the reason modern AI learns. It's the silent engine underneath almost every breakthrough you've ever seen in the AI space. If this video made gradient descent feel less like mysterious AI magic and more like a beautifully simple idea, consider subscribing, because we've only scratched the surface of how intelligence, artificial or biological, really works. Until next time, thank you so much for watching, and as always, don't forget to stay curious.